Okay, I'd like to talk to you about the Orthohack Literalizer. So as you can see, I've run the preprocessor, I've built and run the postprocessor and captured to orthohack.h, and now I'm about to make the literalizer. Let's do that, okay? And let's run it, literal, and we can capture it to ortholiteral.c. You can capture it to any file you want, just not literal.c, which is the literalizer itself. And we're going to look at that in a sec, but let me show you something first. So if you look at ortholiteral header.c, you'll see a series of definitions for these A, B, C, and D operations. So A and B basically run the computation of the binomials. So when you compute a binomial, basically you're taking a so-called numerator and you're multiplying it by a value from the number list. That's number underscore list in orthohack.h. And you take that product and you add it to a so-called denominator at some higher index. In other words, x is greater than w. And you take that sum and you store it as a scalar value, and that is what the binomial evaluates to. And by the way, m means monomial. To me, a monomial is either an original sample point, which lives in the low indices of the monomial list, or it is a evaluated binomial tree, which live in the higher indices of the monomial list. And the first index in the monomial list is always 0. So if we have 64 sample points, then the first 65 points are defined, must be preloaded before we begin the transform, before we begin to evaluate the binomials. So after the binomials are evaluated, we can come back here to the C's and D's, and these actually multiply monomials by values from the number list that I mentioned before, and they add them to a certain coefficient and evict them back to the same coefficient. And then, of course, we have the negative version of both of these, the negative and positive versions of both of these operations. So that's how that works. Now, when you're actually doing the transform, as I mentioned, this is the init. This is ortholiteral init here. All it does is it sets the first monomial to 0. Not very exciting. And then there's a transform. Now C is the coefficient list and M is the monomial list. We use short variable names because the ortholiteral.c can get really huge and the compiler can get very angry about that. So we try to keep our variables tight. Now you'll notice that this file abruptly ends. And that's because in order to actually run a literal transform, we include this ortholiteral header, followed by the actual capture of the literal engine itself, followed by a footer, which is just the end of this transform, which is just a return instruction, essentially. So let's go back now to ortholiteral.c itself. And you can see that here are all the A and B operations to compute the binomials. And by the way, these are fairly order sensitive. So if you want to port this to another language or optimize this series of operations yourself, you must be very careful that you don't load from a memory location that you have not already defined. So that's an important consideration. And then at the end of this file, we basically get into the C's and D's. These can be reordered however you like. All these do, as I showed you, is they pick up a particular monomial, and they multiply it by something out of the number list, in this case the number at index 9, and they add it to some coefficient. And depending on the nature of your transform, you might be able to find and exploit various patterns. Obviously this is going to vary a lot with the transform, but in this case we can see that the same monomial seems to be used 2 times in a row, like pretty much all the time for some reason. And on occasion you can find patterns in the coefficient itself on the side, on the right side here. I've seen cases where, for instance, they differ by only 1. That seems to happen a lot. And finally, there are some few multiplications by 1 that you might want to optimize out. So this gives you the ability to analyze what's really going on and to port it more easily to other languages. Let me just show you in the demo how we actually do a literal transform. So first of all, if you look at the include files, you can see what I'm talking about. You include the header, and then whatever literal transform you want to do, and then the footer. Now, generally speaking, in a deployed product, you would not use a literal transform because it has no loop instructions. So it's very long and verbose and cache consuming. But if you wanted to do it for analysis purposes, if you search for this line, This is the start of the literal floating point operation, transform. I'll go into this more later on my next video about the demo itself, but essentially we allocate a list of coefficients. We allocate space for the monomials, which are the sample points in the binomials. We do this literal init, which remember just sets the first offset of the monomial list to 0. And then we copy all of the sample points into the monomial list starting at offset 1. And we do the transform. It's pretty straightforward in that sense. It is pretty brute force, though, in the sense that there's no loop instruction. So again, generally speaking, you don't want to actually deploy a literal transform, but it might help you to debug it if you want to see it in action. Okay, in my next video, I will show you how to customize the demo into something more like a custom transform that you actually want to use.